We've been working on tons of projects already, so it's always a pleasure working with you guys. So looking forward to this.
Okay, great. So hopefully this has come up okay. So yeah, thank you very much, Stefan, for the opportunity to present, and hello everyone. I'm Ben Russell. I work with HIBAC at the National Physical Laboratory, and very similar format to what HIBAC just presented. Some sort of recent work that we've been looking at and some preliminary results and where we'd like to take it next. But this time looking at Technetium, specifically Technetium 99. So I'm presenting work on behalf of a number of colleagues. So HIBAC, who you just heard from, Elsje Van Es, Frankie Felsen and Peter Ivanov from NPL, and also Ross Allen, a PhD student funded by the Nuclear Decommissioning Authority, who was supervised by the University of Birmingham and NPL, and Yasmin Yu, who from Royal Holloway University, who did a master's placement NPL a couple of years ago. So yes, we'll go straight in. As I'm sure many of you are sort of familiar with, around the motivations for Technetium 99 measurement. It's a long-lived, high-yield fission product. So the environmental mobility of Technetium is of interest to a number of end users, both for decommissioning and for environmental monitoring. There's the table on the bottom right there is a sort of estimate of the Technetium 99 release from various sources, be it reprocessing sites, weapons test fallout, or following nuclear accidents, most recently at Fukushima, which requires sort of quantification in sort of complex seawater samples. And it can be measured using either liquid scintillation counting or a sort of slow increase in measurement by mass spectrometry, most commonly inductively coupled plasma mass spectrometry. And that's been something of interest to us for the last few years, is how we can use, how we can sort of modify the separation to be most efficient when it comes to mass spectrometry based interferences. So just a quick bit of background for anyone who is not familiar with this. So as I mentioned, ICP-MS is being used more and more for measurement of long-lived radionuclides like Technetium 99. There was a very good review, very thorough review paper written a few years ago on Technetium 99, covering all aspects of sample preparation and separation and measurement using mass spectrometry or decay counting techniques, which I'd be happy to find for anyone who's of interest, who's interested in that. But the three interferences in the circles there in the description there is something that is common across most radionuclides to be measured by mass spectrometry. So you have an isobar, which is a stable or radioactive isotope with a similar mass to the analyte, and the detector can't tell the difference between the two. So in this case, looking at ruthenium 99. Have polyatomic interferences where elements react with gases in the plasma. So you can have hydrogen and oxygen from the splitting of water in the plasma, or with argon, for example, as well. So there are a number of examples, but one that is of particular interest is molybdenum 98 hydride. And finally, if you have a high concentration of an isotope, a neighbouring mass, so we tend to look 1 or 2 mass units either side of the radionuclide of interest. In this case, molybdenum 98 is a concern. And there's a few examples there of where mass spectrometry has been applied to Technetium 99 measurement, and what you'll see is that Teva resin has commonly been used in all cases, and what I'll explain in a couple of slides' time is where we've looked at some alternatives that are perhaps, in some cases, slightly more suited to when you use mass spectrometry detection at the end. Just say that there's a number of instrument types. The specific one we have is this Tandem mass spectrometer. So the diagram there shows it. So you have 2 quadrupole mass filters, and in between it you have a collision reaction cell where you can introduce a cell gas to help with some of the removal of interferences that I just mentioned. So what is shown there is the 2 quadrupole mass filters means you get 2 rounds of molybdenum-98 tailing removal. The table on the right there shows the range of cell gases and instrument modes that can be used. That was a lot of work that Yasmin, who I mentioned at the beginning, worked on. What we found was the most suitable was to measure the technetium as a double oxide, because whilst ruthenium would perhaps form a single oxide, which you can see in the row above the one that's highlighted in the blue box, it doesn't tend to form a double oxide. And molybdenum-98 hydride, whilst it does form a double oxide very efficiently, it doesn't form a double oxide with a hydrogen on the end. So you're shifting it to a mass that is no longer an interference. Having said that, whilst this helps with offline separation, in a lot of the samples that we're interested in measuring, it can support it, but it can't replace offline separation. So that support is still a critical part of the method. So with that in mind, we started looking at TK201 resin. So it's based on a tertiary amine structure, and the ion pair agent compared to Tiva resin is weaker. So that means that elution under softer conditions for technetium can be achieved. So what's encouraging here is that we can load our sample in dilute acid conditions. So they're around 0.01 molar nitric acid. So we don't need to acidify the samples before loading them. But what is also beneficial is that we can elute the technetium-99 in dilute ammonium hydroxide. So depending on the study, I've said 0.1 to 0.2 molar there. I believe that the graph at the bottom there from a Triskem newsletter is for the blue bar is 0.2 molar and the orange bar is 0.5 molar. But again, dilute alkali conditions, but crucially we can then load directly onto the ICP-MS for measurement. So we don't need to elute in stronger conditions, and there's then no need to dilute the sample or evaporate it down and re-dilute in suitable conditions. We found this to be very beneficial for testing on some water samples, and also some work we did with Sellafield on some aqueous waste samples as well. It reduced the procedural time that was required. So this particular example, TK201, was an ideal resin for this. But the other thing it led to is it got us thinking about, if we were going to use mass spectrometry for this, how we're going to assess the chemical yield, because there's a few examples there. Again, it's lifted from that same technetium review paper that I mentioned before. There's one example there, but in most cases you're looking at shorter lived technetium isotopes that has to be measured by an alternative technique. And whilst that is absolutely fine, it would be a nice method if you were able to measure the chemical yield and the analyte using the same analytical technique. So this was some work that, as I mentioned, Ross Allen, a PhD student between Birmingham and NPL, looked at, and as I mentioned, the Nuclear Decommissioning Authority sort of fund this PhD and recognised the relevance of this work for tracer development. So he identified technetium-97 as a promising candidate. Is in fact longer lived than technetium-99, sort of just over 4 million year half-life. Technetium-98 is also a good candidate, but our concern was that because it's only one mass unit away, that there is potential hydride or even tailing issues. With technetium-97, it's less of a concern, and if we dilute to appropriate levels, we can avoid a tailing based interference. So Ross has led the work on developing a Python-based coding tool for calculating the most efficient production route for, in this case, technetium-97, but he has in fact done this for a number of radionuclides, and it's a very useful tool for us to have, because there's a number of cases where a good tracer is required. So there was an earlier talk around Neptunium-237. There was some work a few years ago that my colleague Simon Jerome led around trying to produce Neptunium-236. He didn't have access to this sort of capability. Ross went back and had a look at it again and was able to propose other potential production routes for Neptunium-236, for example. But another area of increasing interest is the production of shorter-lived medical radionuclides as well. But in this particular case, the interest was using a stable molybdenum target. So some of the reactions are shown there, depending on the beam energy that's used, and producing ruthenium-97, which has only got a half-life of 2.83 days, and that then decays to technetium-97. So with that in mind, we're looking at it as a sort of generator type approach. So just quickly, so we used the University of Birmingham cyclotron facility to do this, and looked at the irradiation of molybdenum foils, and the gamma spectrum there shows the ruthenium-97 peak. So Ross has successfully trialed this. As I'll come on to explain, the next step for this work is to look at the measurement of actual targets, but I'll come to that at the end of this. So then we looked at potential resins for the separation of this post-irradiation, and this was in fact inspired by a talk at this meeting this time last year from Palatum, looking at technetium-99m produced from molybdenum-99 using TK202, which is based on polyethylene glycol. And I think it was the last Triscan newsletter, gave a nice explanation about how this aqueous biphasic system worked, where anions like molybdenum contributed to the stability of and the structure of sort of water-water interactions, and as a result, increasing the molybdenum concentration actually helped to improve technetium retention on the resin, with the optimal retention in between 5 and 7 molar sodium hydroxide, which in the case of targets, in the case of this study here at Palatum, and in our case as well with a molybdenum target, that's a potentially very useful feature for us to have. And then the technetium can be eluted in water conditions. So this looks very promising. The only thing we had to determine really was how the ruthenium behaved. And so just some initial experiments were carried out looking at 5, 6 and 7 molar sodium hydroxide. Following the recommendations of the talk said previously, the resin was soaked in dilute sodium hydroxide overnight, and then the sample was loaded and washed. It was about loaded in 10 mil, so stayed there, but it was washed in sodium hydroxide, and then finally a water wash to elute the technetium fraction. But in this case, just used mass spectrometry and looked at molybdenum, ruthenium and rhenium. We found that from the few runs we did, that running at a slightly slower vacuum pump rate was a slower flow rate was slightly beneficial in this case. But as I say, these are only preliminary results, and the first thing to look at on the left-hand side is that molybdenum, that agrees nicely with what we saw previously, so that's eluted in the sodium hydroxide fraction. The rhenium on the right-hand side, now that it suggests from this that we get a better retention in 5 molar compared to 6 molar, and then again to 7 molar. But again, these are just preliminary results, and there's some other conditions that we need to look at before we can say that confidently. But crucially, the ruthenium is also eluted in the sodium hydroxide fraction as well. So that is promising, because whilst there's a bit more testing to be done, what it means is that this is our working separation scheme. So you produce ruthenium-97 from your molybdenum target, and we load, in this case we've said in 5 molar sodium hydroxide, and in that case you will elute in the load and the wash fraction, sorry, the molybdenum and the ruthenium-97 will come off of the resin. But any other technetium isotopes that are produced during irradiation, say technetium-98 or 99, will be retained and they're then eluted in water. And that is helpful because it means we can improve the isotopic purity of the tracer. Because if we then wait for the ruthenium to decay to technetium 97, we then repeat the separation. But now that the ruthenium has decayed to technetium, in the load and the wash fraction, again, we removed the molybdenum. And if there was any stable ruthenium present, that would also be lost in this stage. We then switch to water again, and we should then be able to elute a high purity technetium 97 fraction. So in the next stage, really, I'm a bit wary of time, our next stage is to look at these molybdenum targets that Ross has been working on, to see if it stands up for processing of these molybdenum targets. But as I say, hopefully the message I'm trying to get across is that depending on the application, we've got several options with regards to getting a good high purity technetium based separation, in particular for looking at final quantification using ICP-MS. But that was all from me. Say thank you very much again to Stefan and everyone at Triscam for the opportunity to present, and for everyone for listening, and I'll do my best to answer any questions you have. Okay, thank you.
Thank you very much for a nice presentation, as usual. Very interesting work, analytical work, and on the radionuclide production side. And it's always very nice to see that one presentation on one users group meeting can lead to another presentation by a completely different group on a different topic at the next users group meeting. So that's basically what we hope the users meeting are for. So it's excellent.
No, it's great. I don't know if they're here, but yeah, thanks. I mean, that was where it sort of started. So that was very, very useful from last year's one.
Yeah, and it's still it's a completely different application, and still it comes in handy. So it's quite that's very nice actually. Okay, are there any questions for Ben right now? Oh, okay. Talking business. So the question is, do you have any feeling whether you will have enough Tech 97 from irradiation to actually distribute the tracer?
That is exactly the idea. Yeah. So that is we need to produce enough for it to be viable as a tracer. So once we've produced it, we'll then look to standardize it, and then it will be it's not just to see if it can be done. The idea is that we will have a tracer that is for other people to be able to use. From what Ross has done, it looks viable. It looks like it will be produced in enough amounts for that to be the case.
Excellent, thank you. Are there any other questions at the moment? Okay, so if there are no more questions, again, thank you very much, Ben.
Thank you.
As usual, pleasure. And